This is Team 1092 with group members Aneece Douglas, Lexi Scott, and Hannah Wochner. Our team coach is Dr. Matthew Kipper, and we are associated with Colorado State University in Fort Collins. We chose to analyze Problem C, where the dog named Fritz cannot catch different food items that are thrown to him by his owner. This is a common occurrence for dog owners and their pets. We have created a mathematical model to better understand why he is not able to catch these foods and what factors play into his success rate. In order to solve this problem, we had to make a few assumptions. We assumed that Fritz is a 3-year-old male golden retriever dog that weighed approximately 32 kilograms. We also assumed that the food is being tossed at the same force for each item, with the steak weight being 0.45 kilograms, the meatball weight being 0.145 kilograms, the French fry weighing 0.114 kilograms, and we also assumed that the density of air was constant at 1.225 kilograms per meters cubed. And our final assumption that we made was that each food was being thrown at the same angle of 45 degrees. Our goals for this project were to measure the precision of movement of the dog. In order to do this, we took the velocity of the food versus the velocity of the dog moving at the same time scale and compared them. We also wanted to establish the effects of different food success rates, and with this we calculated drag, took into account the air friction, and looked at the different motions of each of these foods. To reach these goals, we have analyzed the video for 3 different types of foods that will be explained later in the video.
We utilized an app called Tracker in order to accurately track the position of the object in both the X and Y direction. This will later allow us to find the velocities of the object in both the X and Y direction, which will then allow us to more accurately solve the ODE. As you can see, we are utilizing this meatball in this example, and we are able to track the meatball with relatively good accuracy, which will allow the ODE to be more successful in order to solve for the object's positional motion. This will allow the position function to be more accurate in terms of the object's actual velocity and thus allow Fritz to catch the next object that we give him. We utilized MATLAB in order to enhance the solving of the ODE. The primary steps were thus. We first pulled all of the data and put it into text files to make it more readable. We then plotted the velocities. We found the velocity fit, and then we utilized that fit in order to solve the ODE while accounting for air friction. Then we plotted this with respect to the position of the dog, which we also found by finding the velocity of the dog's head movement in the Y direction. This will allow us to get an accurate read on how the dog moves with respect to the object, and thus will allow us to analyze what makes the dog successful in catching the object versus what makes him not successful in catching the object. Looking at this in greater detail, looking at this chart, there is an analysis on how we utilize MATLAB to find the solutions. Primarily, we used polyvit and polyval in order to find the velocity components in both the X and Y direction. This will allow us to solve for the positional ODE as seen here. As you can see, the position in the X direction requires an air resistance component, which can be found with the F variable. In the Y component direction, the only negative force would be the gravity and the weight of the object. In this case, it's the meatball. And so if we can find the positional X and Y velocities, we can utilize those in order to solve this positional ODE, and thus be able to track whatever the object is in space. And so we utilized MATLAB in order to first find the component-wise velocities, and then we solved for drag in the X direction. And then we plugged all of those values in to solve for the individual component ODEs. And then we found items like the maximum height and other variables that we found important to the dog's success. And then we utilized these components in order to analyze what made the dog successful and what made the dog fail. And this will be very important in order to compare why the dog fails and why the dog succeeds.
Using MATLAB's polyfit and polyval functions, we were able to find the velocities in the x and y directions from the points found using the tracker. We then found the total velocity using the first equation listed, and then using those found velocities to find the maximum height. To solve our position ODEs, we found the force due to gravity and the force due to drag in order to account for those when observing the positions of the objects versus Fritz. When we first plotted the points the tracker recorded of the stake flying through the air and the points we observed of Fritz's nose, we got these graphs. When looking at these graphs, we can see that the stake was tossed into the air, where it reached a maximum height and then started to move in the opposite direction. When we look at the graph of Fritz, we can see that in the first 2.5-ish seconds, he was not even moving his head slightly to look up at the stake. This shows that he has a late reaction time to the object being thrown at him. This delayed reaction time plays a big part into why he did not catch the stake, since he had so little time to actually be able to track the object. On this slide, you can see all of the solved forces, gravity and drag, that were acting on the stake as it flew through the air. As to be expected, the stake's found drag was the highest out of all of the objects that were observed, since it had the largest surface area. The stake's velocity in the x direction was also the highest because the stake also had the largest mass. With it having the largest mass, that means it also had the largest force due to gravity.
As we can see, the velocity of the meatball aligns fairly well with the velocity of the dog's movement of the head. However, we can see that the dog's velocity does not match up exactly with the velocity of the meatball. This could be a key indication of why the dog fails in catching this meatball. And so we can see that this is a parabolic motion, which means that we are going to use a second order polyfit in order to model for our velocity values. In order to solve for the ordinary differential equation for the meatball, we are going to need a few key variables. Namely, we are going to need the drag coefficient of a cylinder, which could be estimated to be the size of a meatball, as well as the density of the air that Fritz is in, the average velocity, in order to compare with the other two objects in order to determine why the dog is successful in catching the French fry and why the dog isn't successful in catching the steak and the meatball, as well as the cross-sectional area in order to determine drag. We can see that the meatball has a relatively low drag, and this is because the meatball is a relatively small object. We need all of these variables in order to adequately determine why the dog is successful.
After plotting the points from a tracker, we were able to obtain these graphs. As you can see on the left side, the French fry was tossed up, increasing velocity, and then reached a max height where the velocity was 0, and then started to decrease. When looking at the graph on the right side, we can see that the velocities match up between Fritz and the fry. This means that he was able to successfully track the object through the air and catch it due to his reaction time being quick, unlike some of the other foods. This slide shows the calculations for solved forces, gravity, drag, and velocity properties that the fry had while being tossed to Fritz. The drag of the fry is the lowest out of all of the objects, which makes sense as it has the least amount of surface area and least amount of mass.
When solving for the different variables that affect the success rate of Fritz catching the objects, we looked at the max height that the objects reach each time. This image here shows the starting and the ending points of the tosses as well, where point A is the point at which the object is thrown and point C is Fritz's mouth. Using MATLAB, we solved for the velocity and used our assumed angle to solve for these max heights, which on the graph is where the object is at the peak. We developed free body diagrams for each of the observed tosses seen in the video compilation. In the first image, we see the steak being thrown and how the force due to gravity is acting on the object as well as the air resistance. The same can be said in the second image of the meatball and in the last image of the French fry.
These plots represent our solution. It shows the position of the dog's head with the red line and the object position with the blue line as the object is being tossed to the dog. To pull a conclusion from this data, we can tell that when he moves at the same time as the object, he is more likely to catch it. Furthermore, reaction time plays an impact on position of mouth because when he registers faster, he can align himself properly to catch it. As you can see, the graph on the right is the only one with the intersection because the French fry was the only object that was successfully caught. He was close to catching the meatball and matched the movement of it, but was not able to come into contact. With the steak, he did not move his head quite enough to be close to the correct positioning. Another factor of our solution is if height matters. We calculated the maximum height that each of the objects were able to reach using the equation on the slide. From this data, we can conclude that the higher it is thrown, the more time Fritz has to register the object and the more successful he will be. This is shown as the fry reached the highest distance, while the meatball and steak reached approximately the same max height, yet the fry was caught. Overall, height does matter with the success rate of the dog catching an object.
The object size determines the amount of drag. The larger the object size, the more air resistance is going to come into factor. This is why the French fry and the meatball will have a relatively low drag in comparison to that of the steak, as the steak is much more massive than either the French fry or the meatball. The object shape can also determine the initial and final velocities as well as the position-wise velocities of the object. This is because the faster the object moves, the higher the air friction values are. So if you throw something faster, there's going to be more force pushing back on that object. Furthermore, the faster the initial velocity is, the greater the x and y positional distance will be. This makes sense because if you throw an object faster, on average, you're going to make it go higher than if you throw it slower. Therefore, this can be a key indication of why Fritz can catch the French fry, but not the meatball and the steak. Size, the initial and final velocity, as well as the surface area can all come into play when determining whether or not the dog can make the catch. Our model gives a fairly good indication of whether or not the dog is going to make the catch and the key factors for why the dog can't make the catch or why it can. However, there are some limitations in terms of our modeling, as well as some advantages to how we constructed our model. By first creating the ODE and then utilizing real-world data in order to solve that ODE, we allowed that equation to be more accurate to the real-world data. This will go a long way in helping Fritz be able to catch the next meatball. We are also able to track the dog's reaction time in real time, which allows us to very accurately determine how the dog is moving with respect to the object, which we couldn't do if we chose to model the equations a different way. However, there are some limitations to utilizing real-world data in order to solve ODEs. For instance, we cannot accurately estimate the angle of each throw through the video because of the camera angle. This is a real limitation because we essentially had to estimate what the angle was and hope for the best. Furthermore, there are very approximate values for the surface area calculations, as determining the surface area of a meatball is one thing, but determining the surface area of a steak is completely different. And thus, these estimations could skew the model and thus our results.
From our solutions, we found that if the object is not being thrown as fast, meaning it has a slower velocity, the success of the catch was at a much higher probability. With that being said, we also observed a higher probability for the higher the object is thrown at. Giving the object a higher toss allows for the dog to have more time to track said object in the air to allow for a more successful toss. If the object is also smaller, meaning it has smaller surface area, the dog is able to catch it more easily in its mouth. For example, the steak was much too big for Fritz to be able to catch the whole thing in one fell swoop, while the French fry was much easier for him to catch. Also, making sure the dog sees the object and is paying attention to it before it is thrown is very important for allowing the dog plenty of time to track the object while being thrown in the air. Because if the dog was not paying attention, he would have to try and find it and then track it as it's in the air, allowing for a much less time to track the object, leading to a much lower success rate. It also does not hurt to give your dog positive reassurance while performing each of these tosses. For the future, we can teach the dog in question the catch command while also teaching them how to catch, so that each time you want to throw your dog a treat, they will know that they are going to have to try and catch an object being thrown at them. This will allow for the dog to be certain what is happening if he knows what the catch command means. Also, making sure that you are throwing your dog a fair toss each time is important, because if you are throwing an object straight at their face, this will give them very little time to track the object, while throwing it up will allow for plenty of time for the dog to track it. This might take practice and patience, but if you work on your tosses and your dog works on their catching abilities, they will be catching treats and more in no time.